Streaming this on Twitch. Hi everyone. I'm here with Mario Lizcano today. Mario wanted to know more about what's going on with symbolic integers and symbolic floats in PyTorch, and so I thought I'd explain it right now, and also, do a little live stream in case anyone else on the stream has questions about it. Well, I don't know if anyone's going to join us because this is super short notice, but I also make these for the videos afterwards, so hopefully we can do some explaining. So Mario, do you want to start us off with some questions?
Yeah, perhaps the first question is I've seen that in code you've been doing like some changes like rather than calling tensor dot sizes, calling tensor dot symbolic sizes, something like that.
Yep, that's right.
And the question is uh, what will be the extent of these changes? Like, what do you plan to cover? And where will these changes be needed? And uh, should I start using symbolic sizes rather than sizes in future PRs,
Yeah, so
etc.
let's start with this. So the phenomenon that Mario is referring to can be seen in code examples like this. So here's the implementation of copy in PyTorch. It looks very normal, and then we have this diff where instead of saying if self sizes does not equal intermediate sizes, we've changed it into self sim sizes do not equal self intermediate dot sim sizes. And you can see instead of make a call to expand copy, we make a call to expand copy sim it. And what's going on here is the types are different. So previously this function sizes returned an int array ref. So that's just what the it just returns int64s, right? A view onto a vector of int64s. And the new thing returns a view onto a vector of what we call sim ints, which are like integers, but they can also be pointers to sort of arbitrary data. And typically, that arbitrary data is basically some symbolic variable that we're tracking so that we can sort of trace programs that have symbolic shape computation in them. So Mario's question was like, how much of the code base do you have to change? Should I always write code using sim sizes into sizes? And the answer is no, not necessarily. So okay, so rewinding a sec. So why are we doing all of this work, right? Changing all of these, call sites in C++. Well, the reason for it is because we want to be able to trace what shape computation is happening in PyTorch in a symbolic manner. And previously, we were not able to do this because everywhere in PyTorch, we were just passing around integers. And unlike Python, where you can overload the meaning of an integer, in C++ you can't, right? In C++, if it's an int, it's always an int, and you're kind of screwed. And one way you could do this in C++ is you could go ahead and template all your functions so they can either be instantiated with an int or whatever else you want, but that's kind of a pain. So we took this approach, which was that we added a new type, and then we're like slowly changing all uses of the first type, int, into simint. And the key thing, though, to answer this question is we only need to do it when we are trying to trace. So this function copy is actually a composite function in PyTorch. So at the end of the day, it's going to call another function that actually does the dirty work. But if you look at, say, a more normal kernel implementation, like I don't know, Go in native, CUDA. Actually, Mar, you can't see my screen, can you?
I have the stream open the other.
Okay,
Uh,
okay. Well,
there's
if you can
there's a
see it in
little
the
bit of
stream,
lag,
that's cool.
but
Okay. If you look, for example, let me share my screen with you directly so that you can
that
see.
was so much better actually.
Do, 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 do. Uh, Desktop. I'm going to share my entire desktop with you. Okay. Oops. That was not expected. Sorry, just a sec. There we go. Hello, you're back on the stream. Okay. So we were looking at Aten, Circ, Aten, native CUDA. You can see my screen now, right?
Yep.
Yeah, and I'm just gonna pick a
Okay.
random kernel like gridsampler.cu, and there's probably a size call in here. Okay, there's no size call in here, because
There
it's in
were.
CVP, right? So there's probably some size calls here. We don't have to change these because we never actually need to trace into the implementation of a
Yeah.
CUDA function in PyTorch, right? Like sort of the backends are they're leafs, and we're actually replacing the backends with our like custom proxy tensor tracing backend. So you never actually go here. So some parts of
Yeah.
PyTorch don't need symbolic shapes, and some parts do. And we're actually kind of figuring this out because the way we've been working on this feature is essentially we've got this branch, and we've been trying to get models to symbolically trace all the way through one way or another. And we basically find where there's a size call. So whenever there's a size call, but actually the input tensor is symbolically traced, it'll raise an error. It'll say, hey, can't get sizes from a tensor with symbolic sizes. And then we go fix it.
Hmm.
And so, like, there's a ton of places we've noticed that we've needed to update, as you can see in this diff. We've actually landed a
Yeah.
bunch of them to master as well. One more thing is that so typically they fall into a few categories. So one is PyTorch decomposition rules. These typically need to be made to work with Siemens, which makes sense because
Hmm.
like if you ran a PyTorch decomposition with symbolic tracing, you want to be able to see how exactly PyTorch is, twiddling the sizes like in a batching rule to get there.
Yeah.
Obviously, composite functions like copy and the ones here, these tend to need to get siminified because we do trace through them to see what the underlying operations are. And
So
finally,
one question
just one more,
for
yeah, and then I'll answer your
absolutely.
question. Is native functions.yaml? Sorry, no, derivatives.yaml for derivative formulas. These often also need to get siminified. Okay, question.
Yeah, I'm functional manual, I guess. So when you were saying that like implicit functions should sorry composite functions uh, uh, should be sementified, then that's just like composite implicit, right? Composite explicit
Composite
are black
implicit.
box.
That's correct.
Yeah. All
And
right. Good.
also, it's a little nuanced here as well because sometimes instead of cementifying the C++ version, you can write a Python implementation instead. And we've got a few examples of it
Yeah.
here. Do we? Well, so for example, you can write a meta function for a function directly, and then we won't hit. Well, these are not composites, so it's not a great example. But composite implicit, usually it's the most convenient to transform it in C++. So yeah.
Hmm. All right. So to summarize, like most of the cases are going to be like either in backward functions, which basically are composite. Most of like those are
Yeah,
in
backwards are
functional
essentially
manual and
composite.
yeah. Uh, so 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 yeah. Summary would be composite implicit functions and PyTorch code.
Yes.
All right. Cool. Makes sense. Um, All right, so just to understand, like just to make 100% sure, like we had like a magic wand that would program this for us. We would basically cementify all these composite implicit functions, and then like we would be able to trace uh, integers throughout our program. And
Yeah, that's right.
all right, cool. And then I'm yeah about sim floats. What's the context for those? Why do we want sim floats? When do we want to trace
Yeah, that's a good
floats and so
question.
on?
So just to first tell everyone on the stream what a symfloat is. So symfloat is a symbolic floating point number. It's actually double, but we're using the Python naming here. And as its name suggests, it represents a floating point number that you don't actually know. It's derived from some computation, and that you just like you did some compute, and we traced it. And we don't want you to burn in the actual floating point number you computed. We want you to produce a graph that represents the floating point operation indirectly. So the very first time I added symfloat, it was because of this example, actually. So this is the test file for where we test stuff. And I have a test case that I added for this case. Test multiply shape. So what is going on here? Well, actually, no, not test multiply shape. Where is it? Here it is. Test sim into tensor. So what is going on here is here's a function, and this is doing a pattern that's pretty common in normalization functions, which is I have a tensor and I divide it by its shape.
Mm-hmm.
So to actually trace this, what the heck happens? Well, what I want to see is okay, well, I extract out the size from my tensor, and then I do a division between the tensor and its symbolic size, and I get the output, right? This is a pretty normal thing to expect. But actually, when we run PrimTorch, and PrimTorch, for those of you who don't remember, is a way of decomposing PyTorch operations into smaller operations. Hi, Buffet Codes. Thanks for joining the stream. Feel free to post any questions you might have on the chat. Similarly here, so what I did was I turned on PrimTorch decompositions. Kush is here. Kush says hi. Mario. So when we decompose the division operation, what PrimTorch does is it does type promotion. And part of doing type promotion involves actually making the symbolic size have the same D type as the tensor. And so in this particular test, I'm passing in a regular floating point tensor. So PrimTorch says, okay, I need to convert my integer into a floating point number, right? A plain Python int into a Python float. So what happens is we take our int, we turn it into a float, giving us a sim float, and then we do the prim operation on it. And this float is a C10 symbolic float. So we need a way of representing this symbolically so that we can say, oh, we pass in a symbolic float into the division itself.
Mm-hmm. So are there other use cases other than, say, normalization?
Yes, there are. So this was the one that forced us to add symfloat. And then after that, we ended up with a few other examples. So these are mostly all in the autograd formula. So let's go ahead and pull up the functions manual, wherever that is. Kush has a question, which is, what's the stage with PrimTorch as of now? I've been away for some time now. The answer is, it's still going. I think most of the really important operations have already been hit by PrimTorch, but obviously there's a very, very long tail of things to do. And we also have a lot of bugs in our decompositions, so that's a lot of the work that's going on right now. Okay, so here's another example of a symfloat computation in a backwards formula. So this is the backwards formula for var. And what we need to do here is we need to compute, so it's doing the numl, but there's like some correction factor that we're supposed to apply. And then we have to, have that be the reciprocal of a division by 2, and then we multiply it by a tensor. So it's very similar in flavor, but like same idea.
Yeah, it's pretty much like if you have a sim float in the forward computation, something will appear in the backward. Only that not quite, because if you have a backward, it means that the formula is not composite implicit, so you will not need to put sim floats in the forward. But yeah, all right, cool.
Yeah, so in our experience, it's mostly showed up in the backward formulas. I don't think we have any symfloat uses in forwards right now.
All right, that makes complete sense. Because forwards are not composite implicit. There's not very many composite implicit forward functions. Others, in any case, I guess that they will appear in in all loss functions, actually. No?
What do you mean by all of the functions?
Oh no, not loss functions.
Loss
But
functions?
no, like because you call mean, so mean is the one that like you need to divide by n when taking the mean, but
Oh
that's
yeah. So
you
with
just call mean.
mean we don't decompose. What's going on with mean? Probably mean is done in Python. So once we like got division working with symbolic floats, we didn't need to do anything else.
All right.
So you might see a symbolic float in the traced graph, but like I don't know if I have any means in this example. Mean. So we didn't decompose mean actually here. So you're not going to see it in the graph.
All right. All right. Makes sense. So, a couple questions following up on the same discussion. Do we have tests for same and like, say, for example, that someone tells me, all right, implement support for this function with same where should I look? You
Yep.
know, what would be
We
a
have
good,
two main suites of tests. So the first main
all right.
suites of tests is the exhaustive, the make fx symbolic exhaustive tests
Mm-hmm.
in test proxy tensor, and you can see there's a ton of expected failures because we've been working on the operations, and
Yep.
a lot of them are just, hey, there's no symbolic meta function or decomposition for the function in question. So you would solve
Mm-hmm.
one of these issues by writing a decomp or writing a meta function for the function in question.
Yep.
These tests only test forwards, so we also have tests in AOT dispatch. So this is PyTorch test AOT dispatch, and once again, it's another exhaustive test. We have a ton of X fails, and these are running both forwards and backwards. And these are all op info based tests. So if you add op infos for things, we can test them that way.
All right. Nice. Also, uh, you mentioned that. So one way to implement these things is just to change calls to sizes for symbolic underscore sizes or whatever was the name. Another way you mentioned is that by implementing a meta like a decomposition. So if you implement
That's
just
right.
a decomposition or a reference, all this basically like all this is simple. This may be implemented with the torch dispatch or something.
Yeah, that's right. So specifically, when you
Yeah,
register a meta implementation, um, we actually don't use the dispatcher. So you can see this entry has a registered dispatcher false. So what actually
sure.
happens is when fake tensor knows it has symbolic shapes, it will preferentially check if there is a Python meta implementation for a function and use it instead of the C++ implementation because the C++ implementations typically don't support symbolic shapes.
All right. And what I understand is that so when this happens, you are on C++ land, so you come out to Python land, and there's a Python version of the of symbolic ints. I
That's
guess
right.
that's
In
passed
fact, we've
around.
already come out from C++ land to Python land because fake tensor is a torch dispatch mode. And so
Yeah.
that's the point when it goes to Python. And then the Python code just calls into this Python code to actually figure out what the output should be.
All right. All right. Yeah, that makes sense. All right. Yeah, this was very helpful, and I don't have any other question that comes to
Okay,
mind.
well then let's finish off the stream. Thanks a lot for joining us, Mario.
Well, thank you for having me.
Cheers.